So in this video, we're going to talk about drawing out Lewis stat structures for covalent bonds. Okay. Now remember in the last video, we had ionic bonds. That's where you had typically a metal with a nonmetal, and the metal gives up its electrons to a nonmetal, creating a positive ion and a negative ion, where they attracted and bonded that way. With this one, there are no ionic charges. Typically, Lewis stat structures and covalent bonds are typically for two nonmetals. And those two nonmetals, instead of donating and accepting electrons, they will share electrons. So what will happen is the electrons in each of those atoms will rearrange so that they all form in pairs. So for example, we take our fluorine atom, and a fluorine atom has 7 valence electrons. All right, so it has that lone electron there, and electrons like to be in pairs, so it's looking for a partner there. We have this other fluorine atom here with its 7 valence electrons. Again, that lone electron is looking for a partner as well. Now, neither fluorine is going to want to give up any electrons. Just not going to happen. So what we have here, what will happen is, these two electrons, as these two fluorine atoms get closer together, these two electrons will get closer and closer and pair up. So our end result, when all is said and done, we have our one fluorine there, and we have our other fluorine right next to it, and voila, these two electrons are now pairs. They're partnered up. Now right there in the middle, we call that a shared pair of electrons, meaning that that pair of electrons, they count towards the fluorine on the left and the fluorine on the right. They're quote-unquote owned or belong to both atoms at the same time. Whereas the electrons on the outside here, so on the green fluorine here, we got these two, these two, and these two, those 6. Those are unshared pairs of electrons because that fluorine's not sharing these 6. Same thing here. This fluorine, 1, 2, 3, 4, 5, 6. These are unshared pairs of electrons. They only belong to this fluorine right here. And this is our shared pair. Now, one shared pair is called a chemical bond. Or can also be called a covalent bond. And another way to write it, something you've probably seen before, is here's our 2 fluorines, we'll write our 6 unshared electrons on each side, and we will draw a line there. All right. So that line, anytime you have that line, that is your chemical, again, your chemical, your covalent bond. All right, and that represents 2 electrons. So every time you see a dashed line like that, that is a one shared pair of electrons, aka 2 electrons. Now, when we're putting these, we're going to start putting these together, making some bigger molecules. Just some basic rules. Now we'll go over a couple examples. All right, so here's some rules. Each atom, it must have, when all is said and done, each atom must have 8 electrons, shared or unshared. All right, we call that the octet rule, where we say each atom has a stable octet. All right, because remember, what are the most stable atoms on the periodic table? The noble gases, because they have 8 valence electrons in their outer shell. All right, so all atoms want to strive for that stable octet. Electrons must be in pairs. So every electron has to have a partner. So when all is said and done with these molecules, you can't have any single electrons floating around. Now this is key here. The number of electrons in your molecule must equal the sum of the valence electrons in the individual atoms. So, quick example, if we go back up here to fluorine, this fluorine had 7 electrons. This fluorine had 7 electrons. So together, they have a total of 14. Okay, we didn't add or subtract any electrons to get this to complete our octets, right? So you have to keep that same number of valence electrons. That's the key there. Now this last one, so we'll do some examples later on as well. If we need to satisfy these octet rules, we may have to use some multiple bonds. So those are double bonds, so those can be triple bonds. So one example right here, you see the two lines there. All right, this is a double bond. All right, that means it has two shared pairs of electrons, right? Total of 4 electrons. And we'll do a couple examples where you'll see when you need that and how we write that out. So we'll do a couple of basic molecules here so you get the hang of it. Okay, first one we'll do, nice easy one. Carbon tetrachloride. Okay, so that's 1 carbon, 4 chlorines. Okay. So now if we look, figure out what valence electrons we have. All right, carbon starts out with 4 valence electrons. Chlorine starts out with 7 valence electrons. And you have 4 chlorines, so that's still times 4. All right, so 7 times 4 plus 4, that gets you 32 electrons. Yeah, I had the math in my head again real quick, make sure I said it right. So it's 32 electrons, valence electrons. When our compound's complete, you have to have a total of 32 electrons there. So we'll see how that works. All right. Now, if we initially look at carbon with its 4 valence electrons, right, we can write it like that. And if we do chlorine, there's our 7 valence electrons. All right. So as you see here, carbon's got these 4 electrons, and I spread them out for a reason there. All right. Same thing. Chlorine here has a 1 electron. Remember, electrons like to be in pairs. So we have here, these lone electrons. I like to call them bonding sites. Okay, so bonding sites, those are going to want to look for other bonding sites, other single electrons in another atom. So like this electron, it's going to see that one, and they're going to hook up to each other. So if I'll rewrite this, here's our carbon with our 4 valence electrons. All right, so if we show what's going on up here, our 1 chlorine is going to go there, and we're going to add the 7 electrons to that. All right, and we're going to do the same thing with the other 3 spots. Remember, you have 4 chlorines you have to add on here. So there's going to be another chlorine, 1, 2, 3, 4, 5, 6, 7. Here's another chlorine, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And there you go. That's the Lewis stat structure for carbon tetrachloride, CCl4. Okay. And another way you can write it. All right, remember we did lines instead of dots, so we can do that too. Put your carbon in the middle, and instead of putting 2 dots, we're going to substitute those for lines there. So Cl 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So you can write it either way. This one obviously looks a little cleaner because there's not as many dots, but either way is acceptable. And yes, for now, put the electrons around the outside of the chlorine, so we can show that they are there. All right. Now we're going to check over, make sure this molecule satisfies all our rules here. All right. The 2 key rules: each atom must have 8 electrons around it, either shared or unshared. And we have to have the same number of electrons in our compounds we do for the individual elements. So we'll check that out. We'll check that out down here. Okay, if we look at each chlorine here, 1, 2, 3, 4, 5, 6, has 6 unshared electrons. And then remember, this line represents 2 electrons, so that's 2 more right there. So that's a total of 8. So this chlorine has 8 valence electron, or 8 electrons, 6 unshared and 2 shared. And the other 3 chlorines, same thing, 6 unshared, 2 shared. Now, if we look at the carbon here, we're counting these as well because they're sharing a chlorine. So these electrons also count in carbon's total. 2, 4, 6, 8. So carbon has 8 electrons to itself. Okay? So that rule is satisfied. Each atom has 8 electrons, shared or unshared. Now, total number of electrons, said it was 32. So we have to have a total of 32 electrons here. Now, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, how did I count that? 26, 28, 30, 32. So there you go, 32. All right, so there you go. That's how you do carbon tetrachloride. All right, let's do another example here. We'll do nitrogen triiodide. So nitrogen, 5 valence electrons. Iodine has 7 valence electrons. And you got 3 iodines here, so 7 times 3 is 21, plus 5 is 26 valence electrons. So our final compound has to have 26 electrons. All right, so let's check this out. Nitrogen, 3, 4, 5, and iodine. All right. So you can probably figure out where these are going to pair up. So you got that 1 single electron there, and you got 3 of them. So you got 3 of these iodines with those one electron there. Boom, boom, boom. Nice and easy. Nitrogen, 1, 2, 3, 4, oops, 4, 5. And then we're going to put our iodine here. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 6, 7. All right. Or N, I, 1, 2, 3, 4, 5, 6. There's your third iodine. There you go. All right. And double check, make sure everything's the way it's supposed to be. Octet rule and number of electrons. Nitrogen in the middle, 2, 4, 6, 8. We're good there. Iodine, 2, 4, 6, 8. We're good there. Same thing with those two. So everything has 8 electrons. Okay, 26 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. Voila. All good there. All right. So that is how you do Lewis-Dot structures. Those are the basic shapes where it's all single bonds and octet rule. Everything satisfies octet rule with 8 electrons. All right. Now, just with everything in chemistry, there are exceptions, which means not every atom wants to have 8 electrons. Some want to have more, some want to have less. All right. And again, we still have to tackle some double bonds too. So that will be in the next video.